Hi, my name is Tejaswa Rastogi. Very hard to pronounce name, so you can just call me Tej. That's what it is, and that's how I tell everyone to call me like that. So today I'll talk about smart contract phishing. Yeah. So I'll talk about smart contract phishing, and let's just first answer the very basic question: why phishing in the world of smart contracts? So first of all, let's just take a quick recap over what are smart contracts. So basically, if you're familiar with the blockchains, and smart contracts are nothing but just applications on top of blockchains. They are very easy to understand explanation of smart contracts. And why do they matter? Why do they matter a lot? Because we are seeing a rapid growth into the world of DeFi, and we are switching from C5, which is the centralized finance, the way we explore and experience in our traditional world, the banks we have. But in the past, we decided that these intermediaries that we have in some sort of banks and other people are not necessary, right? And it would be even better if we can directly contact or interact with some sort of application, avoiding these intermediaries and having a contact directly, right? Avoiding some taxes and all this stuff. So that's why there are many protocols coming up and serving DeFi and bringing revolution on chain. But with great responsibilities, great opportunities, there also comes a risk. So that's what we will talk about. And the other critical point is like why it's important to discuss and talk about is because these protocols involve like millions and billions of dollars, and that's why it kind of opens door for everyone, like for every user to come up, earn better rewards, much easier than the traditional world. But it also creates new creative opportunities for attackers, right, to launch these phishing campaigns and exploit people and exploit funds and steal money and have fun with it. So yeah, that's what we'll discuss, and we'll have a very practical look. And it may happen that some of these attack vectors may not align very well with everyone's skill, but I'll try my best to explain it in a very simple way so that everyone can get it and bring some new security vectors with them. All right. So a quick bio about me. Well, as you know, my name is Tejaswa Rastogi. What I do, I'm a blockchain security researcher and a security auditor at Consensus Diligence, and my role is to research about new attack vectors, find vulnerabilities in protocols, give them a nice report so that they can save their protocol and save their funds, and that's about it. Besides that, I am a founder and creator of these three things. So CypherShafts is a CDF platform which helps users to learn more and learn blockchain security stuff and also cryptography. And RealSec is again a community for security researchers like us to come and like learn from each other. And now another community which is called a RealSec is now having more than 2,000 security researchers. So that's a plus point for everyone looking forward to get into this field. And the third one is Unchained. So Unchained is a blockchain security conference that I organize every year, and you will find all your famous and well-known security leaders in there as well. And currently my area of research is the zero knowledge proving systems, their security, their integrations and things like that. So if anyone is interested, feel free to contact me and we'll have a chat. So these are the social medias that I handle. So feel free to connect and ping me over anything that you want to discuss. So alright. So let's just start with the agenda. So I have deliberately picked up some very crucial attack vectors in the form of phishing. Why? The reason is I want to put forward like which are so similar that they are very hard to distinguish between. And that's the sole purpose, and that's very beneficial for the attackers to launch some attacks. And we'll see them in action. So here we have on screen is a function in Solidity. Solidity, like if you don't know, it's a programming language that we utilize to code smart contracts. And let's just take a quick recap on how functions work in smart contracts and Solidity. So function in Solidity, the function dispatcher works based on the strings. So here below you will see deposit address unit 256. That's nothing but just the function name, and the hash, like if you hash this function, like deposit the parameters address and unit 256, you will get a 32 bytes string, a hash, and if you take out the first 4 bytes, it will give you the unique identifier to call this function. So that's how the functions work in Solidity. So by having this information, let's continue and try to understand what the function is trying to do. So let's just go line by line. Function homoglyphs. It's an external function taking a parameter called as amount, right? And below, what it is trying to do, it is trying to call an external address called as vault. So, like if you are familiar with DeFi protocols, vaults are nothing but allows you to deposit your funds, and in return, it allows you to earn some rewards or something like that. Just a basic explanation. So here, it is trying to call the vault with this function address or this function signature. So as we just learned that the unique identifier for this function will be these 4 bytes written down, 47E7EF24. So that's nice. Okay, we know how it works. Alright. Now let's just see the same function again, right? So side by side, I have given you a comparison, and if you look pretty closely, you won't be able to find any difference, because both of these are just exactly the same, at least visually, right? But I have highlighted one specific character as A. So that A is not from the ASCII character set. It's coming from the Cyrillic character set, and it's having a different value than the original A we have in English or ASCII character set. Now, if you hash it down, this function, you will get a completely different hash and eventually a completely different identifier, right? So let's imagine this is a protocol and the attacker has created this smart contract calling, just showing the users that this function is gonna call deposit function on vault. What the users will think? The users will think, okay, it's fine, it's calling the deposit function, I'm gonna put my funds in and earn some rewards. But what's happening? It's not actually calling the deposit function. It's calling a completely random function developed and devised by the attacker. And thus, like if you're feeling that okay, I'm gonna put my 100 Ethereum on the walls and earn some rewards, well, good luck to you. You're 100 ETH richer, I would say. So yeah, so this is a quite interesting thing. And why it's important? Because it's quite tough to find out when you're actually reviewing the code, and if you're not actually testing it out, there is, I would say, 90 to 100% chance you're gonna miss this thing. So it's quite important to know that these things exist and how to take care about it. As we're also talking about the defense as well, we'll check how to take care about this thing. Like if we are reviewing, or even we are an end user. So I'm trying my best to explain these things in terms of like how an end user will see that. So let's say you are an end user. So the basic thing that you need to understand that this attack vectors actually are quite complicated in Solidity compiler version 0.6. So in 0.6, it's quite tough to find it out. For that, So there are two kinds of library, internal library and external library. So internal libraries are those like as simple, they have internal functions. External libraries are those which have external functions. So like what are the difference between these two kind of settings? So internal functions are like when you have an internal library, the internal functions are just directly embedded into your smart contract. So we will take a look as well. Let's take them side by side. So on the left hand side, you will find the internal library with the internal function. There is a library math, right? There is a function add, taking two parameters, and as a result, getting the addition of those two values. Simple as that. But the main part that you have to consider is the keyword internal. So that means it's an internal library, and whenever this contract animal will try to utilize this library as line this return x dot add y, so it is trying to utilize the library. For that, the add function will just be copied at this place. So a simple explanation. But on the right hand side, the only difference that you will find is the keyword, right? So here we have the keyword external, right? So what will happen here is basically this function add will now not be copied. Instead, the library will be deployed first, and then it will be used in contract animal as a delegate call. And so delegate call is simply just take it as you're calling a function on some other contract and not on your own contract. A simple explanation. Alright, so let's just talk about how the deployment works in the external library. We now understand that internal library has internal functions, external library has external functions. Internal library functions are just copied, external library is first deployed and then used. So let's just take a look how the external library is deployed and how it works. So the first thing that happens is firstly the library is deployed. Then the 20 bytes address of the deployed library is taken. The original source contract, which is utilizing the library, is compiled. And that library address is now attached to this contract to make a complete contract, right? And the final bytecode is deployed to the blockchain. So what the final bytecode contains is your source contract plus the attached library, right? Now let's just take a look over the contract verification on blockchain explorers. So blockchain explorers are the most crucial tool given to end users and even for the developers as well, that you can actually see what the bytecode is all about and not blindly interacting with some random contract. You can actually see, okay, this is the source contract and I can read the function, I can try to understand it, and if I find it like fine and then well managed and no possible flaws, I will go ahead and interact with it, right? But if you have just a bytecode, you're just playing a blind date and a blind game with some strangers. So with either scan, like how it works, when you deploy your bytecode, while verification, it asks you to give the exact source code for the bytecode, and it compiles it again and try to match it with the deployed bytecode. If both of the bytecode matches, it gives you the verification. Okay, the provider source code is fine, I will verify the contract, and now you can read the code, right? But what will happen in the case of external library? Because we don't have any information of the library, right? The only information we have in the source code is the address, is the target address of the library, right? So what we can actually do, instead of giving it the actual library, let me just give it a very random and a malicious library, right? So let's just take an example of that. So the first file that you are seeing, libgambler.sol, it's a library, right? And if you see the function roll dice, you must be seeing a lot of things happening. Let me give you a summary. So it's just, let's take an example. example of a casino, right? Let's take an example of, or let's take example of a lottery game or something, right? So it's expecting you to provide a random number, and if the random number matches, you will earn the reward, so you will get the lottery, simple as that. And for the same reason, it is trying to generate a random number, kind of rolling the dice, and whatever the value or whatever the outcome will be, if you provide the same value, you will get, and you will get the reward, right? So now the user know what the logic is all about, and the user can go ahead and try to understand it and try to try his luck and give the exact same random number and try to win the money, like on the lottery. But that's not how we have decided to go into. So lib gambler here, the address you are seeing, is the address of the library which is attached to the contract. But that library is actually containing a different code than the one that you are trying to interact with. So the above code that you are trying to interact, this is the logic which you are seeing, which you feel that's the actual code which is generating the random number. But actually, the attacker is trying to add another parameter called as sus with it. So it's making a sussy library for you, and even if you know very well what the code is all about, you will still fail because you don't know what the actual function that's being called, and the attacker is still able to phish you, even if you have all the information about the smart contract, even if you have all the information that's public to you. So that's another interesting campaign which attackers may try to phish you. So it's very good to know, like, if you have this information. So again, how we can find it out? Just check. Just go to your either scan or just go to your protocol address, whatever smart contract you are interacting with. Just check which one is the library, and if there is any linked library, right? And try to match the code. And if both of the code matches, then you can still be satisfied that yes, I'm interacting with the right contract and there's nothing malicious happening with me. So again, a good example. Third one, it's a pretty interesting vector because it's so hideous that even if you know the smart contract, even if you find out there's no linked library, even if you find out everything is working fine, you have all the public information, all the source code, but the attack is still possible, right? So let's just understand what it is all about. So for it to understand, we have to understand what is metadata, a smart contract. So metadata, like as the name says, is the metadata about the smart contract, like the compilation information, the source code hash. Let's say you have a smart contract X, so it gives you the information like, okay, which compiler you have used, what was the optimization, what was the hash of each and every file, right? So the purpose of this metadata is, if you get this metadata hash, you can try to verify yourself that the smart contract has actually been compiled the right way, and what you are interacting with is actually the same contract by verifying the metadata, right? The reason is, if the attacker tries to change tries to even add a single white space, the whole hash will change and the metadata will not match with the original smart contract, right? So that gives the end user a surety and a way to verify by themselves that whatever they are interacting with, whatever they are trusting is actually the real actual smart contract, and nobody is trying to exploit you, right? But let's just have some fun with it. Okay. So first of all, let's just take a look at what metadata looks like. So this is the bytecode, right? When you compile your smart contract, you will get the bytecode, obviously. The So let us try to understand the metadata itself. So that coding is called as CBOR, or concise binary object representation. And this is how it's encoded. I'll give you a quick summary so that you don't need to brain out on this thing, but yeah. So the important part is you have to check this string, right? This long string. So it's of 32 bytes, and it actually contains the IPFS or swarm hash. So what are IPFS and swarm technology? They are just decentralized servers. Like we have servers in the Web2 world. So these are kind of servers in a decentralized world, just storing your files, information, and things like that. So it is kind of an IPFS hash or a file stored at some server location, right? Which is hosting your configuration file or this metadata, right? A simple summary. So this is a hash string for a file located somewhere on a server, and basically hosting this configuration file, the metadata for you, so that you can just fetch the file and verify, okay, it is actually confirmed and everything is working fine, right? But since this hash is actually not the part of the contract bytecode, or not a crucial or important aspect, or not a mandatory, I would say, parameter. Like even if you ignore this metadata completely, your bytecode is still fine. Your contract is still fine and will work the exact same way. So you must be wondering, if it is like that, then I have the capability to basically add anything and everything, right? Because if it's not, like if it doesn't matter to the verification, let me just play with it. Basically, you're right, and you can do that. So for that, we need to understand some other crucial vectors or crucial parameters for it, like how external and internal functions work. So for external functions, the idea is simple, as we all discussed. We have the 4 bytes unique identifier, right? We discussed in the very first attack vectors that every function is identified by 4 bytes. So the external functions are found or dispatched by these 4 bytes. It tries to match it out. Like you give it a transaction, it takes out the call data and tries to match it out, okay, whether the call data that you have passed or the function that you're trying to call, whether I am having that function or not. A simple strategy. You give me 4 bytes, I'll try to match it down with the possible function that I have in my code, and if anything matches, I'll give you that function to run it down. A simple information. Internal functions are a bit different. Why internal functions are different? Because they are not needed, they don't need this jump strategy or this call data strategy that you should give me the function signature and I will try to find it out. Basically, internal functions are known at compile time, so it doesn't need all these kind of jumps and instructions. So what it can do, it can basically grab jump dispatchers, and whenever you are calling a function and it is trying to interact with an internal function, it can just directly jump to it, right? There's no complications. There are not no complications required, right? So alright, so let's just take an example that we have a smart contract or a protocol, right, which is giving users the capability to provide function pointers instead of just function names. Yeah, it's a bit impractical approach. You will not basic example, and there's nothing there's nothing more besides these four functions on smart contract, right? So you have the information that the only function available are x and y, internal function, and these are the only functions that I can call, right? And what they do, they just return 3 bytes of hexadecimal value, simple functions, right? But as we have just learned and discovered that you can utilize metadata and you can basically add anything, any random hexadecimal value, any random, even EVM instruction, or even the functions themselves. So basically, so this thing we have already discussed. Since IPFS hash are not mandatory, or the strings that we have seen, the long string, that metadata is not necessary and not at all required if you don't want to. It's just complementary for the users to verify and have that transparency on the chain. But if you're having it, you can just have any random string, any random value, because it doesn't take part in any verification. So you can have the smart contract verified, and you can have literally any random value, any random metadata. So with anything, what we can do, we can basically encode an entire internal function, right? So earlier there were just two functions, x and y, but the attacker decided to encode another function as z in the metadata itself, right? And for the users, even for the security researchers, you will not have this idea that this can be done as well. You're just reviewing the code, what is given to you, and it looks fine, it works fine. There's no possible attack vector, but still the attacker decided to encode in the metadata, which is completely unattached to me or the security reviewers, right? So this is example implementation of that attack vector, right? So consider the value highlighted in sky blue. So what it is trying to do, it is a simple EVM instruction set, which is storing 1 at slot 0, just an example. But this is to give you some sense that it can be done as well. So what if, let's go back. So we knew that if the user passes 100, it calls function x. If the user passes 200, it's called function y. The user don't have any other information. But the attacker knows if I pass 1337, I can still call function z, which I know about, which I'm the only conveyor, right? Which I'm the only one who can understand and exploit it, right? So that's it. And the attacker can call function z and utilize and do whatever he or she wants without knowing or without telling anyone what's happening in a smart contract, even after giving all the public information that is required, right? So that's so hideous and quite complicated, right? I can understand, but I just wanted to share so that you can see how it works. So for the last one, I will make it pretty simple so that everyone can just easily understand it. So as every language has some built-in functions, right? Like Python has built-in functions, Java, and take any other language you want. Same as that. Solidity also has some built-in features and functions. So what if the attacker tries to phish choosing those existing and built-in functions that nobody never thought of that it can be done as well, right? Let's take an example of that. So here, the block number and and the first line that you're seeing is actually the feature of Solidity. And what it provides, it gives you the block number of the network, right? So that we know about. And second, the line data block, right? So that line, what I'm trying to do, I'm shadowing the built-in feature of Solidity with a custom defined feature that I have made. So now if I call block.number, which is struct, it will not call the network feature or the built-in security feature. It will call the function or the parameter defined by me. So I have actually overridden what basically the language is giving me, right? So what the user will understand, okay, it's just the block.number, which is the network parameter, and that's how they get the block number. So it will just always work fine because nobody can do anything with that, right? That's a system-defined function, right? But actually we have overridden that thing, and now it's custom, and now it's in control over by the attacker, right? Same goes for this required check. The line you're seeing, required number is greater than 100, right? Requires nothing but just if else condition, right? So you're just checking if number is greater than 100, then it will work fine. Otherwise, it will give you an error that is number is not greater than 100, right? Pretty simple, right? So this is built-in feature. This is built-in security language feature. But what I have done below, if you check this function requiring tender, so what I have done, I have kind of overridden the built-in system-defined feature of security with my custom feature, right? So even if you are trying to understand that the function will not work if I give a number like less than 100 or something, right? But you can actually define a custom logic and literally avoid that out, right? And the user will still feel that's how the system is supposed to work, right? So this another attack vector and another very crucial thing and very new, like very less people know about these things, that these things can happen as well. So with that, my motivation was to promote awareness about the smart contract as well, because that's kind of a very rapidly moving tech stack. Everyone wants to jump onto that. Everyone wants to be a smart contract security researcher, auditor, and even for the end users as well, right? We know that in Web3 we can kind of play with a very large amount of money and numbers, but if we don't know like the basics of security, we can be trapped, right? We can be exploited by the attackers, right? So that's about it. Final conclusion that I want to say. This is for end users. First of all, the very first point is you should not be interacting with unverified contracts, obviously, right? As we already discussed, it's like a blind date, right? If you don't know about the strangers, I guess you should not interact with them, right? That's the first thing, because until and unless you don't have that expertise, you can decompile and decode the code and try to understand whether the code is actually fine and not exploiting anything, you should not be interacting with it. That's the very first tip you should be following. The second thing is, even if the code is very